This is a differential rate law, or what's just called rate law problem. So the first thing they want us to do is write the rate law expression for the reaction. And so I'm just going to go look at the data, and I'm going to see that A stays the same for trials 1 and 2. And so what happens then is whatever changes in rate is because of B. So I'm going to take a look at B, and I'm going to divide the 0.48 divided by the 0.12. I want to see that that equals to 4. So I know that 4 to the x, 4 raised to the x, is going to equal whatever happens to the rate here. And so 8 divided by 2 is 4. So I know that easily x equals 1. So the order for B is going to be a first order. So I'm going to go ahead and kind of set up. So I'm going to put B. I don't need to write a 1. If you want to, you can, just so you know you've done it. I know that rate is equal to K, and then we're going to see if there's any effect for A. So right now we know that the order for B is 1. So now I need to look and see where does B stay the same if that happens, and I can see that the effect on rate is all because of A. So that does happen, which is so nice. And so in a couple different places, actually just trials 2 and 3, that's where B stays constant, so all the effect on rate is due to A. So I'm going to divide the 0.24 divided by the 0.12, so that equals 2. And so using the same process, 2 to the x, and so I know that this change is 2 to the x. And so what happens over here between 2 and 0.5, so I know if I divide 2 divided by 0.5, that's simply 4. So easily again, and I love it when it's this easy, that 2 to the x equals 4, so we know that the order for A is going to be 2. So that's our rate law expression for this reaction. So then to calculate the value, we know that this occurs at 30 degrees. So that's the only reason why they gave us the temperature, is that we need to calculate the constant K. I usually just pick the first experiment or first trial and plug in the numbers. So I'm going to do that and solve for K. So I know that using the first trial that I have 8. Because it says moles, liters to the negative 1, I'm just going to call that molarity. So molarities, hours to the negative 1. So I can kind of follow along with my units. And so that's going to equal to K raised. And so I'm going to take the value for A, which is 0.24. And that's molarity, raising that to the second power. And then B, 0.48. And that's also molarity, and raise that to the first power. So when you plug everything in, I'm going to end up with K, and if I multiply all this out, it comes out to be 0.0276, and then following my molarities, it's molarities cubed. So then I'm going to take that number and I'm going to divide it to solve for K. So very simple algebra. So if you solve this out, I see that my molarities will cancel one of the molarity down here. I'm going to move everything to the top, and so my unit is going to be molarity to the negative 2, hour to the negative 1. And then if I divide that out, I end up with approximately 289. I'm going to round it to just 3 sig digs because of the data that's given to me. So this equals to K. So I know my rate constant is 289, molarity to the negative 2, hours to the negative 1. So that's my answer to B. A good double check on that is I see my overall order of the reaction is 3. So 2 plus 1 equals 3. And so I know the unit for K will always be 1 down from that to the negative. So there's molarity to the negative 2. So that works. So that's 3. So then the next question on C is they want us to just plug into that formula. And so I can see up here that for experiment 6, which they're asking me for, they give me some numbers and I know my values. And so again, rate equals K, A squared times B. And now I know everything but rate. And so K, 289. And I know that A for the reaction and that's going to be squared. And I know B was 1.35. So we would just plug all the numbers into it and solve for rate. So when you do this, you end up with the answer as 0.765 molarity hours to the negative 1. And that's going to be the rate of the reaction. Now, for the last question, for D, it's really not a rate law problem. And so what they want is they want us to look at experiment 2. So we go up to experiment 2, and we look at this information. And I'm going to just refer over here to the chemical equation and just write some things down. So I know in experiment 2, they're giving me 0.24 for A and 0.12 for B, and they're asking me for C. Well, I can instantly see, and they're asking me for that final molar concentration, keeping the conditions the same. So if we take a look, I can see who my limiting reactant is going to be. I know I need twice as much B as I do A, because the relationship is 2 B's to every 1 A. Well, I don't even have as much B, so I know that that's going to be my limiting reactant. So it's going to be based on that. I know that I get 3/2 C for every 1 amount of B. So I'm going to plug in B's number. And then I'm just going to calculate that out. And we end up with a 0.18 molarity. So that's going to be my answer for D. Just a simple limiting reactant stoichiometry problem. So this is an example of a AP chemistry, just a plain old rate law or differential rate law problem.